Assalamualaikum. So today my friend and I want to present experiment 5 for GC, and the title of our experiment is Analysis of ethane 1,1-CBs using gas chromatography in various sample. So this is our objective for this experiment, and basically this objective is based on journal that we have reviewed, and our main objective is to determine the retention time of ethane 1,1-CBs in each sample. So for the sample we have choosing four sample, which is mango juice, orange juice, kaki juice and carrot juice. Second objective is we want to observe the chromatogram peak in every sample, and third objective we want to state the functions of each component that contained in GC instrument. I will start with the introduction first. Gas chromatography is a technique that widely used for separating components based on their differences of boiling point or molabilities of a compound. The principle of this instrument is a carrier gas is being compressed in a container, and from compressed container it will flow throughout the column with optimum flow rate. Using microshrink, we inject our sample in GC column, and normally our sample is in liquid form. Sample then travel to column by carrier gas and being separated in this column. Next, it's being detected by detector and displayed in terms of chromatogram in readout. The methodology of this experiment is first we need to read the shrink that we use before filling it with the sample. It is very important to avoid any chemical that can present at the surface of shrink, and the volume of the sample may be more than the required volume. You also need to tap the shrink gently if there is a presence of any air bubble. We need to hold the shrink vertically, needle up, and the plunger is pushed to the required volume at eye level because of the detection is so sensitive. We need to wipe off the outside of shrink to make sure there is no excess on the needle. After that, we can inject our sample in the GC column, and don't forget to switch on the GC and set the GC with suitable conditions. How to inject the sample? First, we place the shrink using both hands on top of the injection port, and with one motion, push down through the septum, push in the plunger, pull out and press the button start, and lastly, your spectrum will be recorded. And this is the example of GC instrument that we use in this experiment, and the right side is its schematic diagram, where inside this instrument is actually where the column is located. So now we move to the result, and the result that we obtain is based on the online sources. So in this experiment, the analyte or compound that we want to observe is ethane 1,1-CBs, and the sample that we choose, as you can see in this table, we are choosing mango juice, orange juice, kaki juice and carrot juice. And this is the retention time for each sample, where this retention time is referring to the time for analyte to pass through the column of the time between the sample injection and an analyte peak reaching a detector at the end of the column. As you can see here, this is the chromatogram separation for each sample that we have observed. So here we have chromatogram for mango juice, orange juice, kaki juice and carrot juice.
Okay, Assalamualaikum. My name is Nur Shamira. I will proceed with discussion, conclusion and reference for experiment 5. Okay, let's move to the discussion. Through the experiment, the retention time of the analyte ethane 1,1-oxybase could be identified by using gas chromatography method. Gas chromatography is the most common method that being used to separate the chemical compound of the sample mixture and then detect them in order to determine their presence and how much they are present. This experiment involved the gas-liquid chromatography type, where the mobile phase was gas and the stationary phase was liquid. As the sample being injected to the injector, the sample were passing through the column, then the analyte can be detected by a detector. Based on the result obtained, the retention time of the analyte in mango juice, orange juice, kaki juice and carrot juice were 2.30, 2.18, 2.46 and 4.18. Through this, we can see that the retention time of the analyte in carrot juice was the highest value. This happens because the compound separation is based on the various strength of the compound's interaction with the stationary phase, and the longer it takes to migrate. In other words, the retention time becomes longer. So, there are several factors that affect the gas chromatography separation. First is volatility of compound. Second, polarity of compound. Third, column temperature. Fourth, flow rate of the gas. And number 5 is length of the column. So let's move to the schematic diagram of the gas chromatography method. We have gas carrier, pressure regulator, injection port, column, and detector. Gas carrier can transport analyte through the column. Pressure regulator, it will supply constant gas pressure. Injection port, where the place the liquid sample is vaporized and being transported onto the column by the carrier gas. Column is the place where the separation occurs. And lastly, detector, it will detect and quantify the different components of the sample as they emerge out from the column. So let's move to the conclusion. In a nutshell, this experiment helped us to understand well about gas chromatography method. There are advantages and limitations of gas chromatography method. The advantages are it has high resolution power compared to the other method. It has high sensitivity. Also, it has high accuracy and precision. And lastly, it can save our time as the analysis of sample very quickly. For the limitations, many chemicals may have the same retention time. Not all the sample may be separated. Unknown compounds have no reference retention for comparison. Okay, for the reference, we will use one journal from the Google and 2 other websites for our reference. Thank you.
Assalamualaikum. I am Anis Safia and I will be presenting my part of Experiment 6, High Performance Liquid Chromatography or HPLC of caffeine content in tea. So, what is high performance liquid chromatography? It is a technique used for the separation of a substance to determine the quantity and identity of its components. It works in the same way as column chromatography, but more advanced. The solvent is forced to the column under high pressures, and as a result, the particles have a greater surface area during the interactions between the mobile phase and the stationary phase, which leads to greater separation. The time it takes for each specific component in the solvent once it leaves the column is a retention time and is its identifying characteristic. For this experiment, we have 3 objectives, which is to determine the retention time of a standard solution, which is caffeine solution, to identify the caffeine peak area in a tea sample, and to determine the amount of caffeine in tea sample using response factor solution. This is our concept instrument. As you can see, the flow rate of mobile phase is at 0.5 ml per minute. Our column is C18, 150 mm times 4.6 ID at 0.45 micrometer. Our detector is ultraviolet at 254 nanometer. Our mobile phase is 50 millimole potassium dihydrogen phosphate, acetylnitrile, and methanol. Our ratio of mobile phase is 40 to 8 to 2. For sample preparation, caffeine is isolated from tea by having 5 grams of tea solid in a 500 ml beaker with a 225 ml distilled water and boiled for 10 minutes. It was then filtered using a Buchner funnel. 25 ml of 10% lead ethanol solution was added to the filtrate and boiled for another 5 minutes and filtered again. The tea solution was poured into a 500 ml separatory funnel on a ring stand and 30 ml of CHCl3 was added. It was then shaken until it is uniform. The layers are separated and the lower layer was collected in a 100 ml beaker. This step was repeated a second time and collected into the beaker. Anhydrous sodium sulfate was added into the beaker containing the extract and heated for a short period of time in a water bath at 70 to 90 degrees Celsius until white crude caffeine was obtained after 24 hours. The crude caffeine was purified and recrystallized using chloroform, toluene, and petroleum ester by solid phase extraction. To determine the caffeine content in tea, the isolated purified caffeine sample from the tea was dissolved in 100 ml of mobile phase and filtered through a syringe filter of 0.45 micrometer with a 5 ml syringe. 20 microliter of the sample was injected into the column and the trace recorded. The relative peak areas for the sample were obtained and used to determine its concentration by calculating from the calibration curve. This is the operation of HPLC instrument. As you can see, the HPLC solvent goes to the HPLC pump, which then goes to the injector alongside with the sample. The injector then forces both the sample and the solvent into the HPLC column, which then moves to the detector, which then records the retention time, and this data is sent to the computer. The waste sample is then removed. And this is the result. As you can see, there is the calibration curve of caffeine standard solution and the caffeine determination of green tea, black tea, and coffee by HPLC. In this case, we only focus on green tea and black tea. This is the calculations. As you can see, we calculated the peak area of caffeine standard, the response factor, and the concentration of green tea and black tea. This is further discussed by Shakila in the next part.
Bismillahirrahmanirrahim. Assalamualaikum. My name is Nur Shakila binti Ramli. I would like to present about discussion and followed by conclusion for HPLC. In this experiment, we have learned about development of high-performance liquid chromatography (HPLC). As we know, reverse phase HPLC become more common of a standard mean of HPLC separation compared to normal phase. Here, reverse phase was used, meaning that mobile phase are potassium dihydrogen phosphate, acetonitrile, and methanol, which are polar solvent. The mobile phase elution known as isochronic elution, where isochronic solvent consists of potassium dihydrogen phosphate, acetonitrile, and methanol with ratio 48:2 respectively. This is because the solvent composition remains constant throughout the elution. Basically, HPLC is used to determine the retention time of caffeine peak in tea sample, and the amount in tea sample using the response factor solution. In reverse phase, the retention time will increase since composition of mobile phase is strongly affected the retention time of the analyte to be eluted throughout the column. We can say that the most polar compound will spend the much time in the mobile phase and move more quickly, and vice versa. Caffeine can be detected within the UV absorption range of 210 nanometer and 275 nanometer. In this experiment, a wavelength of 255 nanometer was chosen to measure the elution caffeine using UV detector. The longer retention time depends on the interaction of the analyte with the tertiary phase. Next, for preparing calibration curve in HPLC, 10 to 60 ppm caffeine standard were used to identify peak at retention time around 6.18 till 6.22 minutes. The logs of the curves were 56659 was used for determination of caffeine in each sample. From caffeine standard curve, known as calibration method, as can see the line of best fit goes to many points, produce a very good R-squared value, which is about 0.9922. To find caffeine content in our sample, we need to find the peak area of caffeine using linear equation of calibration curve for caffeine. And all the calculation were shown on the previous slide. Using response factors formula, which is peak area of caffeine divided by concentration of caffeine. Then for concentration of each sample, just calculate average peak area given for each sample divided by response factor value. So by do this calculation, we got exact concentration as shown in the table. There are several precautions in this experiment, such as sample must be degassing properly to remove dissolved gases and dust from the liquid, and avoid formation of bubbles so that the measurement of reading column not being affected. Then shrink must be rinsed and cleaned before and after injection to prevent any contaminant. For conclusion, we'll be able to determine the amount of caffeine in black tea, green tea, and coffee using the response factor solution. After we identify concentration, standard caffeine with its peak area to get response factor solution, we can conclude that retention time as a qualitative measure and peak area as quantitative measure of caffeine samples. Lastly, HPLC is very versatile due to its ability to easily spread a wide variety of chemical mixture, but error can occur due to the overloading of the sample. There is some references that we use to finish our HPLC video. That's all from us. Thank you.